Infinity, something that even the best of us can struggle with. Is it a number? Is it a concept? Or is it none of the above? Or is it both of the above? Why does it behave in such a strange way? And how do we be careful that we do not get manipulated by this phenomena? Let's look at 3 different problems, all of which are connected by infinity, and work through them together to try and get a better understanding of this abstract idea. You have been drafted to participate in a strange race. The goal is to cover a distance of 2 units, but you can only run half of the remaining distance each time. So you start at 0, then cover half of 2, which is 1. From here you move on to 1.5, and then on to 1.75, and then so on and so forth. You're getting closer to 2 after each step. But the question is, will you ever technically finish the race? According to this animation, you can get very close but never finish. However, let's return to this later and move on to an even more strange concept. What if I told you that the sum of all positive numbers is equal to -1/12? Let's start by looking at a different series. If we look carefully, there are 2 ways we can arrange this sum. One of the ways will give us 0, and the other way leaves us with 1 as the answer. This is called a Cesaro sum, and we get 1/2 as our final answer. Now, we will consider a different series. If you write this series S2 again, but in a slightly different way, moving all the terms to the right by 1, we can add them up together and get the formula 2 times S2 is equal to S1. We already know S1, which means the S2 is going to be 1/4. Now, let's go back to the main series, which we will call S accordingly. If we consider the difference S minus S2, we end up getting the multiples of 4, which is actually exactly 4 times the series S. We do some rearranging and get S is equal to -1/12. But does this make any intuitive sense to you? There are more real numbers between 0 and 1 than there are integers between 1 and infinity. This is called the counter-diagonalization method, and what we do is write out a list of numbers between 0 and 1. Now, our new number is going to be the nth decimal place digit in the nth term. So for example, we will take the first digit in the first number, second digit in the second, third digit in the third, and so on and so forth. Our result will be a new number each time that was not in the list before. Now, looking at 1 to infinity, any number that you mention can be tracked on the number line, no matter how small or large the number is. So, how does this make any sense? And how does this relate to the previous 2 examples? The common denominator in all these 3 problems is the concept of infinity and how we deal with it. Math gives us tools to think about all these problems, but first we need to stop thinking of infinity as any other number and start utilizing the tools that we have. Going back to the first animation, using this logic is not a good idea. With this logic, you will have never-ending chocolate or never-ending debt to repay. What we do is we use limits. Now, limits are a very simple concept to understand, but very important in maths. I'll give you a simple example. If I ask you what number this expression is approaching as x goes towards 2, you will tell me 4. Now, approaching is a word that I use loosely, and there are more rigorous ways to prove a limit, but you get the idea. With the race in question, we can express it as a limit in summation notation, and we will see that indeed using this logic now, it makes sense that the answer is 2, and that we will end up finishing the race. If you don't believe me, you can search it up. It's called Zeno's paradox. The point of showing you this was to bring to your attention that sometimes we can be easily manipulated when working with infinity. So where is the mistake, you might ask? Well, there are convergent series, and then there are divergent series. Convergent series are those that approach a certain number as we keep on adding more terms, while divergent series are those that will never approach a specific constant. The mistake in this summation was to assume that this series even has a value. When we give numbers to things that cannot possibly be pinned down by 1, we're asking for trouble. Instead, we call this a divergent series and continue on with our day. Something that might surprise you is that there are different types of infinity. Not all infinities are the same, and this problem is the perfect example to showcase this. Between 1 and infinity, no matter what number you choose, I will eventually count unto that number, even if it might take me a very long time. However, between 0 and 1, no matter what 2 numbers you choose, I can always give you a number that lies in between those numbers, and this is called uncountable infinity. There is nowhere to stop, and therefore, in some senses, this is a larger type of infinity than the countable infinity. The idea behind this video was to clear some misconceptions about infinity, and to raise awareness that we cannot treat it like any other number. Let's give infinity the respect it deserves by learning more about it and doing our own research. Finally, please remember to like and subscribe if you haven't done so already, and thank you for watching.